This is the first section of Lecture 11, which covers the Internet. Then the very beginning of Chapter 11, there is a history of the Internet. Make sure you take a look at that. I'm not going to say anything about that in this lecture, but I will be talking about what networks were combined to make the original Internet, what an intranet is, and then what makes a global Internet possible. What is the Internet architecture? As we know, the beginnings of the Internet traces all the way back to the Soviet launch of the Sputnik spacecraft. And so as a response, the U.S. government was a little bit worried, because if you could launch a satellite, obviously you can launch a nuclear missile. And so ARPANET was developed. ARPA was Advanced Research Programs Office, and they were specifically focused on developing space capability, the ability to do intercontinental ballistic missiles. But of course, they started to get interested in satellite as well. But what they wanted through a ground network was the one that was survivable, and that was when the ARPANET, or the Advanced Research Programs Agency Network, was developed. So this was the very first iteration of the Internet. It's called ARPANET. So ARPANET was actually established in 1969. So this is 1969. ARPA itself, as a research institution, was developed in 1958. So this was 1 year after the Sputnik launch. And so in 1969, ARPANET grew, and ARPANET was predominantly, or was, a packet switching network connecting mainframes principally between UCLA and Stanford universities. However, as the packet switching matured a little bit more, it was turned over to the National Science Foundation in 1981. And so in 1981, it was under the management of the National Science Foundation, which then established between 1985 and 1995 a larger NSF net, which included San Diego, Boulder, Colorado, Champaign-Urbana, Pittsburgh, and Universities of Princeton. At about the same time, there was another network, and this network was out in Michigan, and this network was actually called MERIT. And the MERIT stood for the Michigan Educational Research Information Triad, and it consisted of the Michigan State University, University of Michigan, and then Wayne State University. And this was established way before, in 1966, once again, to connect mainframes. And so eventually what happened is MERIT, in 1995, essentially took over this entire network. And so MERIT, in 1995, was actually MERIT plus NSFNet. And then, of course, eventually, as the Internet became more and more popular and a decision was made to actually commercialize parts of the Internet, it became a service provider capability, or your Internet service providers, or ISPs. So as I mentioned before, IP creates a survivable network, and so we have to make sure that we know that this is not the same as reliable network, because of course a reliable network is one that will make sure that you get delivered all your packets and that it's going to be delivered in a sequential order. And the IP standard doesn't allow that. However, it does guarantee a survivable network, which means even if you come up with a network congestion or a partition, your information, your packets could actually flow in different directions. And so, as an example, let's take a message, and we're going to have this message, and what we're going to do is we're going to break that up into 5 different parts, like we've done before. So this would be 1, 2, 3, 4, and 5. And so when we send it, we can send it to different paths through the network. So one might go through here. Let's say if this was A, sending messages to H, as an example. 2 might follow the same path, but 3 may go a completely different path, and then 4 may go down here, and then finally 5. So in this case, we've taken 3 different paths. And so in the case of a network partition, say D, node D was taken out. and so D is no longer in the network. Well, you can see that we've lost a couple packets, but we certainly haven't lost all of our information. We still sent packets 3, 4, and 5, and as a result, most of our information is going to survive, and if we need to ask the sender or the source to send those packets 1 and 2 over again, that's a lot better than having to have the source send the entire message over again. So this is what we mean with when we talk about survivable networks. There's a simple difference between intranet and internet. If we look at a intranets are private networks. And so all of the devices, the configurations of all the devices will be controlled by the organization that owns the intranet. So there's a lot of large organizations that would like to essentially control all aspects of their IP network, and so therefore it's called an intranet. And of course, we all know what an internet is, and the internet, of course, is the public network. So this is public. And many times what you'll find, depending on the purpose of the intranet, you'll have ways, like say through gateways for a private user on the intranet to actually connect in and get a proper IP address to start doing any kind of work over the internet. So let's look at the internet architecture. And we know that the internet architecture, we're talking about the network layer, or layer 3. So this would be network layer. And as a network layer, we know that we're going to provide end-to-end connectivity. So let's say you have an internet service provider. An internet service provider can be any commercial firm whose business it is to provide internet access, and then they're going to have an autonomous network or autonomous system, which is an IP network that they control, and so they control all the configuration of the routers. So let's say we have an ISP, and let's say this is ISP A, and they're going to have an autonomous network or an autonomous system, and they control their network, they configure it, and then they actually provide services to any subscriber who may want to connect up to their autonomous network. Let's say we had another autonomous network. Let's say this autonomous network is ISP B. And of course, once again, they have their own autonomous network or autonomous system. And so we have a user, let's say this is user 1, wants to connect up to user 2. How did they do that? And so the real question is that because we're at the network layer, despite the autonomous networks, despite any of the data link networks underneath, user 1 should be able to contact user 2. And so we have to have some kind of connection between these two autonomous networks. And so what we have is a facility that's called today it's called an IXP, and this is the Internet Exchange Point. And before, the previous name was the Network Access Point. But in any case, these are fortified actual physical structures that provide different ISPs to come in so that they can exchange IP data. And so IP data from one go through an IXP or NAP, so this is also NAP, and then go into ISP-A to get to user 2. And so this is all transparent to user 1 and user 2. All they know is as long as they have an IP address of the destination, they can actually communicate back and forth, despite the fact that they're actually going through two different internet service providers. So these IXPs or network access points are pretty robust facilities. They cover layers 1, 2, and 3. And of course, they can actually connect more than just two ISPs. They could connect several ISPs. So you might have an ISP C out here, maybe even a D. And so through all of this, you have all these service providers coming into this facility to exchange internet packets. Now, in the beginning, when they did this, of course, they're separate organizations, and of course, they have separate billing, so they wanted to ensure that the accounting in the books are correct as far as how much data, how much it's going to cost. And so, for a while, they started to do this, and they tried, but unfortunately, because of the whole overhead of accounting, it actually turned the internet into a very slow network. And so they all got together and they said, "Hey, let's forget about all the accounting and let's just exchange packets without worrying about how many packets are going into one network or out of another one." And so they agreed to this, and this is called peering agreement. And so with a peering agreement, you don't have to worry about the accountability of packets going back and forth. All you really need to know is that you have correct IP addresses, network IDs, host IDs, and that's taken care of at the international level. And so with these peering agreements, no longer did any of the ISPs have to account for the data, and therefore the actual speed of the internet actually improved by quite a bit. So the IXPs are there. They provide the layers 1, 2, and 3 connectivity between ISPs or autonomous networks. And they also serve a lot of other purposes. But if you've ever seen one, like there's one in Florida called Terramark, it's quite a facility that has its own power generation in case of emergency. And so if a hurricane came across Miami, sure enough, Terramark would still be standing. Now, since the internet had its roots in the United States, of course, the U.S. Department of Commerce administered the internet all the way up until 1998. In 1998, because the internet has grown so much and became an international capability as opposed to just a single country's capability, the address blocking or the distribution of address blocks was given over to a non-governmental organization called ICANN, and ICANN stands for the Internet Corporation for Assigned Names and Numbers, and one of its departments, IANA, which is the Internet Assigned Numbers Authority. So this is important because of the fact that we want to have a hierarchical IP addressing system in which the numbers can tell you which region of the world the address is coming from or going to. And so this hierarchical type of organization, similar to the telephone system, makes it very easy and very quick to find the destination and know who the source is. So it made a lot of sense to have some organization that would provide some kind of standardization to the addressing itself. The other part was, of course, standardization. And so the standards were still the two main organizations that were responsible for the standards, of course, are W3C and IETF, which is the Internet Engineering Task Force. In this section, we talked about the networks and what networks combined to make the early internet. We talked about the reason why internet was a survivable network using datagrams and the difference between internet and private intranet IP networks. We also talked about ISPs and how they develop autonomous networks or autonomous systems, which could either be public or private, and that in order to satisfy the network layer end-to-end connectivity, we had to have essentially facilities like the IXP, formerly known as the NAP, to actually bring together all these autonomous IP networks through peering agreements so they could actually exchange and share IP datagrams. And then finally, we talked about how we need to distribute blocks of IP addresses in a hierarchical manner so it makes sense, and so that we could always tell source and destination regions of these IP addresses. Internet address protocols, and we're going to talk specifically about IP version 4, the classful, and the CIDR addressing. And of course, CIDR stands for the classless interdomain routing address. And then we're going to talk about the hierarchical scheme of the IP and how it works. On the slide, we see the IP version 4, which is going to be a 32-bit address. And so this address layout is the same whether we're talking about classful or CIDR addressing. And so we take the 32 bits, so this is 32 bits, but we're going to divide it into 8 bits. And so you have 8 bits here, 8, 8, and 8. Of course, that's going to equal 32 bits for the address, source or destination address. And so since all of these X's represent either a binary 0 or a 1, what we can do is it's easier, instead of just talking about 32 ones and zeros, talk about a decimal value for an IP address. And that's why we typically just change from this 8-bit segment here, or octet is what we call it sometimes, into a decimal value. And so to do that, we have to take a look at the most significant bit of each segment. So we can see down here that we have the most significant bit on the farthest left to the least significant bit, which is on the farthest right. And since we're in base 2 math, it's going to be 2 to the 0, 2 to the 1, which equals 2, 2 to the 2, which equals 4, 2 to the 3, which equals 8, all the way out to 2 to the 7, which is 128. And so if we were to place 1s on all of these places, the bit places, so we had 8 1s, we would get a number. Of course, 2 to the 8th is 256 different permutations of that number. Of course, 0 is one of the permutations. So a legal decimal number of a binary segment is going to be either between 0 and 255. So you will never see a IP version 4 address that's going to be higher in any one of the 8-bit octets that is going to be greater than 255. So let's take a look at an example and say we were given this binary IP address. So how do we turn that into a decimal value? Well, of course, we see the first one is going to be in the 2 to the 7th or 128 most significant bit position, so we just put a 128 down here. And then we see the second one is going to be in the 64th position, so then we put a 64 here. And then we see that the remainder of the bits are going to be 0. And so 128 plus 164 equals 192. And we can do that for each one of these places. Like, for instance, this is at 128. This is in the 32nd position, and this is in the 8th position. We add those up, and we come with 168. Same thing for here. We see it in the 8th position, and in the 2 position comes up to a 10, and then same thing for this last octet. So our decimal value for our RP address is going to be 192.168.10.10. Now, before we talk specifically about the IP version 4 class addresses, let's talk about the differences between a network ID and a host ID. So as an example, with IP version 4, you have a 32-bit address, and that address is going to be divided into 2 parts. The most significant bits are going to be the network ID, and then followed by host IDs. And so the host ID would be like a subscriber number. It actually identifies the endpoint or a server in between or device in between. So that would be the host ID. And the net ID tells you what network that device is on. And so let's take a look at a quick example. Let's say you were given an address of 124.250.64 and 72. And let's say that this was your net ID, and then the remainder of this was a host ID that belonged to a specific device. And so the way that this actually works in a hierarchical form is, let's say that you have 2 networks here, and one network had a net ID of 124, while the other had a net ID of 125. So as a result, in looking at this address, instead of having to look at both the 124 network and the 125 network, it immediately knows that the device is going to be hosted on the network ID that's identified as 124, and therefore then only has to take a look at this network to determine where this host is. So just like the telephone system, it's a hierarchical way of getting to the destination very quickly. So for classful networks, let's compare the sizes of the A, B, and C. So if you were allocated a Class A network, that means that out of the octets, only the first octet would be the net ID, but the remaining 4 would then be allocated to hosts, so you could actually assign those to your users. So if this is the case, and this is 8 bits, and this is 8 bits, and this is 8 bits, that means the number of hosts that you can actually support is going to be 2, and so 8 times 3 is to the power 24. Of course, we're using the 2 because we're in base 2 math. We're going to minus 2, and we're going to talk a little bit about why we minus 2, but one is for the net ID, and then the other one is for broadcast. And so this gives us 16,777,214 hosts that we could actually support with the Class A network, which happens to be the largest network. Now, if we look at the Class B, now what we find is that the first two octets are going to be the net ID, and then the last two are going to be the host. And so now we only have 16, so this would be 2 to the 16 minus 2 equaling 65,534. So you can see that a lot fewer hosts than if you had a Class A network assigned to you. And then finally, the Class C, which is the smallest, where the first 3 octets are all going to be the net ID, and the very last one will be the host. And so obviously this will be 2 to the 8th minus 2 equaling 254 hosts. So obviously you can see that if you're given a Class A, you're a huge network. You can assign a lot of addresses out of that. If you're Class B, a little bit, medium size, and then of course Class C, you're a very small network. Let's take a look at the Class A network. And as a side note, one of the easiest ways to tell whether a classful address belongs to a Class A, B, or C network is to look at the first octet. And so we'll see that as we go through all the classes. But of course, when we talked before, Class A had the largest number of IP hosts assigned to it, so therefore it would be a block, a class address that was assigned to a large network or a large ISP. Now, to identify a Class A network from other class networks, we take a look at the first octet, and there will be a 0 placed in the most significant binary position within that first octet. That means you're going to have a 0 here, and then the remainder of the octet can be pretty much a 0 or a 1. So if we want to take a look at all the numbers the first octet can actually support, we would just say that would be all zeros to zeros and then all ones. So 1, 1, 1, 1, 1, 1. And if we were to turn these two into a decimal value, then this of course would be a 0. Now this is in the 128th column, and we know that an octet is going to be a maximum 255. And since we have a 0 at the 128, we subtract 128, and that gives us 127. Now these are in the first octet. Unfortunately, 0 and 127 are reserved, so we can't assign them out as a Class A network. And so 0 is reserved, and 127 is reserved for loopback testing. As such, the range of Class A networks that can be assigned would be from 1 to 126 in the first octet. So now let's talk about making it easy for our computer to identify that an IP address belongs to, in this case, a Class A. And so this is where the subnet mask comes in. And so the subnet mask is going to be a value that's going to be kept in software on your computer. And so when it sees this subnet mask of 255.0.0.0, it knows it's a Class A address without having to determine whether that first octet is within the range between 1 and 126. And so the subnet mask, in this case, is 255.0.0.0. So essentially in computer speak, if you look at 255 in the first octet, you're looking at all ones, followed by zeros in the remaining 3 octets. And so this tells you that this is a Class A, because this is going to be your net ID. Now let's take a look at a quick Class A example. So let's say you were given the block 124.0.0.0 that was assigned to you. So you know that you're going to have the range between this all the way out to 124.255.255.255. Now, the net ID is always going to be the lowest IP address within your range. So the net ID in this case is going to be 124.0.0.0. The highest range is always going to be broadcast. So now your broadcast is going to equal 124, and let me change that, 255, 255, and 255. What that means is that your usable host range is going to be from 124.0.0.1 to 124.255.255.254. So this is what you can actually send out to your subscribers or to your devices. So how many hosts can you support? Well, the hosts that you can support is essentially going to be, because you're using the last three octets that are going to be assigned to hosts are going to be 2 to the 24, because 8 times 3 is 24, minus 2 because you're subtracting the net ID and the broadcast, and as such, you're going to have 16,777,214 IP addresses that you can distribute out. And of course, since we're talking about a Class A address, your subnet mask will be 255.0.0.0. Class B networks are the next largest, and so it's going to be the first 2 octets of the IP address that is going to represent the network ID. So if you have the 4 segments, like we had shown before, then it's these 2 that are going to be the net ID. And then the last 2, which are going to be the host ID. And the way we identify Class B is because there's going to be a 10 placed in the most significant bit positions within the first octet. And so if we take a look at 10, now this is going to be once again the first octet, and then of course we could have 000000 as the lowest address for Class B, all the way out to, once again we have to use a 10, but then we could fill the rest up with ones. Okay, in the first octet. And so if we take a look at this, then we know that this first number, since this is at the 128 position, will be 128. And then we take a look at this, and we say, well, now we have to take a look at the only positions that's missing is now the 64th position. So this essentially be 255 minus 64. And let me do this math real quick. 255 minus 64 gives us 191. So in the first octet, if you see a number 128 to 191, then that's going to be representative of a Class B address. Now we look at the subnet mask and we see that, just like in this picture up here, the first 2 octets will represent the network ID. The last 2 octets will represent the host ID. So since the first 2 octets are going to be our Class B network ID, the network IDs or Class B network IDs that can be assigned will be anywhere from 128.0 to 191.255. So that'll be the range of Class B addresses that can be assigned. So now let's do a Class B example. So let's say you were given the following block of addresses, a Class B. You were given a 190.24. So that's the address assignment or the block assignment, and you know that you can go all the way from 190.24, all the way out to 190.24.255.255. Now, the first thing is the lowest address is going to be the net ID. So your net ID is 190.24.0.0. And you know that your broadcast is going to be the highest IP address, so that becomes 190.24.255.255. And therefore, the number of hosts that you can support in your Class B network is going to be 2 to the 16, since it's only the last 2 octets that can be assigned for host IDs, minus the net ID and the broadcast ID. And so this gives you a number of 65,534 hosts that you can actually send IP addresses to. So your host range, in this case, will be essentially not the net ID and not the broadcast ID. So we would say it's 190.24.0.1 all the way out to 190.24.255.254. So these are the ranges of your host addresses. And of course your subnet mask would be essentially 255.255.0.0, because you're going to have binary ones placed in the first 2 octets. Finally, let's take a look at the Class C network, which is our smallest network as far as class networks go. And so this time our net ID is going to be the first 3 octets, and we're going to have a 110 placed at the most significant bits of the first octet, even though the first three octets are going to be the network ID. And then we're going to also have a subnet mask of 255.255.255.0. So let's take a look at this. We're going to say 110, because we're looking for range here. So 000 all the way out to, once again, 110, and now we're going to place everything with ones. So we know that this is going to be 128, and then this is going to be in the 64 position. So 128 plus 64 is going to equal 192. And then we take a look at this, and we know that this is going to be in the 32nd position. So it's essentially 255 minus 32, and this gives us 223. So if we want to see the range of Class C networks, then we take a look at the first 3 octets. We know the first octet, the lowest one, is going to be 192.0.0, all the way out to a Class C network that's going to be 223.255.255. So just as we did with the Class A and B, let's take an example of a Class C network. And so let's say you received a block assignment, and your block assignment is going to be, this is going to be an example, 221.16.17.0. So you're given this Class C address, or Class C network allocation. And so you know you have a range from 221.16.17.0 to 221.16.17.255. And of course your net ID is always going to be the lowest address, so that'd be 221.16.17.0. Your broadcast will always be the highest, so this is going to be 221.16.17.255. The number of hosts you can support is going to be 2 to the 8th minus 2, so that becomes 254 hosts. So you can see that's a pretty small number of hosts or addresses that you can actually send out. And so if we want to take a look at the host range, then we would take a look at the lowest number, So it'd be 221.16.17.1 to the highest number, 221.16.17.254. So this is your host range. And then, of course, finally, your subnet mask would be 255.255.255.0. So this is a handy table that appears in your textbook, identifying the classes, what the most significant bits in the first octet look like, as we had discussed in the previous slides, and then, of course, the binary range of the first octet and the decimal range of the first octet, and then the number of hosts supported by each one of these class A, B, and C networks. So as you can tell just by looking at the differences between A, B, and C, that there's not a lot of, like say for instance you needed a network assignment that was somewhere in between a B and A. Well, there's not a lot of flexibility built into this classful system, and so of course the CIDR notation allows us to have that flexibility, and the CIDR notation is something that is an IETF 1993 standard for representing IDs, allowing an easier way for IANA to distribute large blocks of IP addresses. Not to mention that if you're the owner of a large block of IP addresses, it allows you to subnet or even break down that block into smaller networks, which is called subnetting. And doing this really kind of helps you as far as your searching, being able to hierarchically get to your source and destination very quickly. With the CIDR notation, we still have to identify what the network ID is from the host ID. And the difference between the class and the CIDR notation is that we're not stuck with just going with a class A, B, or C. We can say how many bits from the left to right that we want to represent our network ID. And so as an example, let's go ahead and look at a binary number. And so this binary number is going to be a 00111, 1101, and then 0000, and then 1010, and then a 0001, 0100, and then finally 0000, and then 0001. So you can definitely see that we still have the 4 octets here. But let's say we just wanted the first 10, and the way we represent that we want to have 10 bits from the left to right become our network ID is that we use a slash and then the 10, the number of bits from left to right. And so in this case, we can see that we count over 10 spaces, we come over here, and so this ends up being our network ID, while the remaining 22, so this is 10 bits, and the remaining 22 bits becomes our host ID. Okay, so how would we actually, how would this look if we were actually doing this in decimal value? And so let's go ahead and convert each of these, and so we're still going to keep them as 4 octets. So we're going to take a look at this first octet, and when we do the conversion, this first octet becomes essentially a 125. The second one becomes a 10, and then 20, and then 1. And so our IP address is going to equal 125.10.20.1, but since we want the first 10 to represent the network ID, we do go /10, and so now we're in CIDR notation. So here are our IP addresses from the previous slide in decimal format or CIDR format, and then the binary format. And of course, we said the first 10 places are going to be our subnet ID. So this is our subnet ID. And we also said that the lowest, since we're talking about the host address here, we're saying the lowest number in the block is going to be the subnet ID. So we're actually looking at 125 dot, and in this case this is a 0, that's a 0, and then that's a 0, so .0.0.0. So that's our subnet ID. The next thing that we have to do is we have to take a look at what our broadcast is, and that our broadcast ID is going to be the highest number in the block. And so in this case, this is still 125, But now we're going to replace ones all along here. So these last two octets are pretty easy. This would actually be 255, and this would be 255. This one's a little bit different because two of the bits are not included as part of the host ID in the second octet. So we're going to have to subtract 128 and 64. So this essentially becomes 255 minus 128 minus 64, and this gives us 63. So the broadcast ID in this case, and let me move this down here, is going to be 125.63.255.255. So let's take a look at how many hosts we can actually support. And of course we have 22 bits that are going to be the host ID. So therefore we're going to have 2 to the 22 minus the subnet ID and the broadcast ID. And so this gives us a total of 4,194,302 hosts that we can actually support. And of course the host range is going to equal one above the subnet ID. So this is going to be 125.0.0.1 all the way out to 125.63.255.254. So that's our host range. Now, last thing we have to take a look at is what is going to be our subnet mask. And if you recall, if we have a subnet mask, we want to identify the network ID by placing ones in every position in the 32-bit address that is going to be part of the net ID. And so in this case, we have 10 bits from the left to right that are going to be the net ID. And so the first octet, which is the first 8 bits, that's pretty easy. That's going to be 255. But then if you take a look at the 2 zeros here, and then you place ones on each because they're part of the net ID, then that's going to be essentially 128 plus 64, or we get a total of 192. And then, of course, the remainder is going to be a 0. The remainder octets are going to be 0 because of the fact that those happen to be our host IDs. And so now this is our subnet mask. There's another example that's in the textbook, and I encourage you to take a look at it. And it'll give you a little bit more insight to how CIDR works. So this slide actually shows that extra example that I was talking to you before in the previous slide. And so this asks a little bit of different question. You're given an IP address and you're asked to see how many different subnets you could actually identify. So the this is the actual address, and so the address would actually be 192.20.210.62. And because we're going all the way out to the 27th bit as our network ID, then this would be a /27. So this kind of gives you an idea of how that would be divided between the network ID and the host ID. And then the next slide, get to the next slide here, shows a table that tells you out of a /27 how many subnet IDs you could actually create. And in this case, you can see that you can create 8 different subnets, and then here are the subnet IDs, the subnet masks that go along with that, the host range in decimal form, in binary form, and then the host range in decimal form. So go through that. I think it would be a good exercise in helping you understand CIDR a bit more. In this section, we talked about the differences between IP version 4 classful versus CIDR addressing. We talked about subnetting and what subnet masks were. We talked about the differences between network IDs, host IDs, and broadcast IDs. We talked about the host ID ranges, and then we determined how we could determine the number of possible host IDs within a host range. We'll take a closer look at the IP version 4 datagram format, and then we'll also talk about some other protocols. We'll also talk about some of the major differences between IP version 4 and IP version 6. And then we're going to talk a little bit about what MPLS is. So this diagram is the format for the IP version 4 datagram header. And so after this header is the actual information that you're sending. So you can see this is going to be 32 bits wide, and we have 6 rows. And so I'll just go through some of the more interesting fields. As an example, version. So this will tell us that we're either IP version 4, as an example in this case. The header length, the total header length is going to be 4 bits long. And then we have other things such as the total length of the datagram in length in bytes. And so even though this is a 16-bit field, it represents the number of bytes. So if we take a look at 16 bits and we determine how many bytes we can actually represent, that'd be 2 to the 16, and then this will equal 65,535 permutations, which also represents the number of bytes. That's the total length of the diagram. So you can see that a datagram, a packet, can be up to a little bit over 65,000 bytes total. So say you have a size of your datagram, and so the datagram goes through the network, and of course there are going to be some parts of the network which may want to fragment your datagram even further. And so this identification that's 16 bits long is used for when the IP datagram is going to be fragmented, so that you know that when it reaches its destination, it's been fragmented. Now, if you don't want your fields to be fragmented, then you use this 3-bit flag, which says that even if the datagram becomes too large for the network, this datagram should not be fragmented. Following that, you have the time to live. This is just so that you don't have a datagram that goes into an infinite loop within the network. Sooner or later, you want it to age out so you don't contribute to network congestion. And so that's what this time to live is. It just tells you, in this case, how many hops from router to router that datagram can actually survive until it's just taken out of the network altogether. And then you have the header checksum, which really is a checksum error detection of just the header itself, not of the data. And then finally, probably the most important two would be the source and destination addresses, which of course are 32 bits long. So let's talk about IP version 6. And one of the most noted things about IP version 6 that it is not backward compatible with IP version 4. And so this was one of the things that the working group said that they should have realized and should have done. Of course, that doesn't mean that we don't have IP version 6 in our network today, because we really do. But we just have to do an address translation and a protocol translation within the IP network. It's not all that difficult to do, but if it was in a perfect world, then it would be perfectly backward compatible with IP version 4. Now, this came out as an IETF standard back in 1995. So back in 1995, that was still in the early days, and so they were talking about looking at some kind of follow-on to IP version 4, especially considering that they knew that the 32-bit address of the IP version 4 was not going to be sufficient enough to provide everyone the IP address. So it was something that they kind of looked ahead at and knew that they were going to run into that type of a problem. Now, the other question is, when we look at the 128-bit address, which is the large extended address for IP version 6, when we look at it in forms that we can understand, then it becomes a hexadecimal representation vice the version 4 decimal representation. And so this makes a lot more sense than the decimal representation, because of the fact that here we have in this table, computers are going to be binary, and because they're binary and they have to translate between, the IP address in decimal form, if it was version 4, it made a lot more sense for that translation to be hexadecimal instead. And the reason why is because it's more natural. If you look at, say, for instance, octal or base 8, this is going to be 2 to the 3rd. Hexadecimal is 2 to the 4th. And so hexadecimal is also used in Ethernet MAC addresses, as an example, 48-bit addresses. But then version 4 is a base 10, and there's really no equivalent here. So you can see that the math between binary up to decimal is a little bit more difficult, not straightforward. And so you want your translation between the IP address and the actual binary address that the computers and the networks use to be more natural. So they say that IP version 6 makes more sense to be represented in hexadecimal form. So another improvement of version 6 over version 4 is the fact that its header is more simplified than version 4. And it will also support things such as IPsec with an extended header, which is going to be required on the IP version 6. Now, they have different types of modes of data exchange. And, of course, with IP version 4, we, of course, had a point-to-point, but we also had broadcast. So broadcast was essentially a message that went out to every node within the net ID. In this case, with version 6, we've replaced broadcast with what we call multicast. And with multicast, we still have an ability to go out to a number of nodes on the network, but only within a subgroup of the nodes. So we don't have to broadcast to everybody. And then, of course, we have things such as unicast, which is just the exchange between two nodes, and then anycast. And with anycast, this is a information that's going to go out to more than two nodes, and it's going to guarantee the shortest, least cost paths, and the cost being defined as either the time or the number of hops or other metrics that would be used to make the path more efficient. So this is the simplified header of the IP version 6. So we have the version, once again. Then we also have a traffic class, and this is used to identify the different classes that IP version 6 will actually support. And then we have the flow label. And so this flow label essentially gives you information on the sequence of the packets for specific source and destination messages, whether you're using unicast or multicast in this case. And then, of course, the payload length. So this is just the length of the IP version 6 payload. The next header case, so this identifies if you have an embedded protocol or header within the IP6, and so you would identify this header by using this extension right after the source and destination addresses to tell you what this new header is and the length of the header. And then, just like you had time to live on IP version 4, we have a hop limit for the number of hops that this IP version 6 packet can take. And then, of course, once again, source and destination addresses, this time 128 bits long. For the IP network, of course, routers are going to be the smart devices that are going to know the best routes to the network to take. But in order to do that, it's going to have to share information on particular routes, congestion, network partitions, those kinds of things. So that's what the gateway protocols are all about. So we have border gateway protocols that enable the exchange of routing information so that you can actually efficiently send data based on any kind of cost metrics, whether this is going to be the amount of time that it takes, the number of hops, the distance, or any other kind of metric that the routers will actually use. So the border gateway protocols will actually use transport layer 4 to send routing information, and so that all this routing information is shared by all of the routers within the network. And so this is very different than a switch, which is really just worried about the port-to-port or link-to-link forwarding of any kind of data link information. With the router, you want to have the ability to pick out the best route through the routing network. We have two major categories of border gateway protocols. We have the internal BGP, and then we have the external BGP. So how do they work? Well, in an autonomous IP network, we're going to have to share the routing data within the AN, and so therefore we're going to use IBGP. Of course, if we wanted to connect up to another autonomous network through an IXP, or an Internet Exchange Point, then we're going to have to share routing data with that external autonomous network. because of the fact that if we're talking about a network layer protocol, we're talking about end-to-end, despite how many different autonomous networks we have to go through. And so in this case, we would actually use external BGP to share that routing information so that we could get the best route for our datagrams through the other autonomous network and any other autonomous networks that we have to transit to get to the destination device. In order for network routers to understand where to forward a datagram and what best route through the network it should take, it has to have routing tables. And these routing tables can be constructed statically. So in other words, a static routing table will be manually controlled, so manually added or manually changed, versus a dynamic, which is going to be automated. And so we have protocols which will go around to update all the tables within the network. And some of these protocols are called RIP, OSPF, and then EIGRP. Let's talk about the Address Resolution Protocol. And the Address Resolution Protocol ensures that there's a close mapping between MAC addresses at the data link layer and the IP address. So as an example, if you had an Ethernet local area network and your intention was to communicate to other local area networks outside through the internet or a network layer protocol, you would probably want to have a stack, an IP stack associated with each one of your nodes. And so if we take a look at this example where we have node E, and within his config file, he's going to have his own IP address. He's going to have the network address, and so this is the network ID of the network that he happens to be on, a subnet mask. And so the subnet mask tells you that this is a class C network. And then should E want to communicate to another local area network through the internet, it would have to have a gateway in which it could send its data to this gateway in the event that it goes outside of the local area network. So in this case, we see that E wants to send a message to C, and C happens to be, by just looking at the IP address of C, is within the same network. So there's no reason to forward that data over to the gateway. That information can just be sent within the network, even though there's still an exchange between the IP network and the MAC address in this case. So in this case, all of the Ethernet nodes has an IP address associated with it. But of course, we have to remember that each one also has a MAC address associated with it. So E would have a MAC E address, and then C would have a MAC C address. And so Address Resolution Protocol would actually map C's MAC address to C's IP address, and the same thing for node E. And so in this case, you really didn't need the IP address, and if the intent of the Ethernet local area network was just to communicate within the network itself and never to go outside of the network, then you wouldn't even need the IP stack. But in this case, there's also always a chance that one of your nodes wants to go out and communicate through the internet to another device, and if that's the case, and you know that ahead of time, then you're going to equip all of your nodes with an IP address. Now let's take a case of where node E wants to communicate outside of its local area network to X, and of course knows what X's IP address is. So the first thing is that you'll note that the address of X is not within the same network ID, and so therefore it's going to use and send that data to the gateway router. Now the gateway router in this case is connected up to the Ethernet LAN on which X is going to be located. And so it sends the information to X's local area network, but it may not know the MAC address associated with the IP address. If there had been previous communications, then it'll know the mapping of X's MAC address to X's IP address, and it'll keep that in its cache. And so any further data that has to be transmitted over to X will be automatically sent via the mapping to the MAC address. However, if it receives the IP address and it doesn't have that mapping in cache, then it has to go out to broadcast to all of the nodes within the local area network in hopes that one of the nodes will actually claim that IP address. And so in this case, X would claim that IP address, and so then the mapping between X's MAC address and X's IP address will be kept in cache just in case additional datagrams are going to be sent for X. The Dynamic Host Configuration Protocol was established as an IETF standard in 1997. And it's a client-server protocol that assigns IP addresses from a block of ISP addresses. So each ISP has their own block of addresses that it can actually send out to its hosts. And this protocol operates over UDP, which is the Transmission Control Layer Protocol. Now, there's a couple of ways that the assignments of IP addresses can be made to host devices, and one is a manual allocation, and through a manual allocation, it'll be up to the system administrator to actually assign every device its own IP address. And of course, even intermediary devices, such as the gateway that we saw in the previous slide, has to have its own IP address. So for a very large ISP, you would have a system administrator having to change over or assign IP addresses over literally hundreds of devices or more. So another way that DHCP can actually help in distributing the IP addresses is through automatic allocation. And so through automatic allocation, permanent IP addresses can be distributed automatically without the need for a system administrator intervention. So this is good in the sense that if you have, like I said, large even intranets where you have thousands, hundreds to thousands of devices, you certainly want to have an automated way to actually sign the IP addresses, because that could take quite a bit of resources if you didn't have this protocol. Now, one of the things that we've seen is that with the IP version 4 addresses becoming very limited, there must be a way to somehow reuse IP addresses, and that's where dynamic allocation comes in. And with dynamic allocation, IP addresses from the ISP's block of addresses are assigned dynamically for the interim of the period that a user needs an IP address. So they don't own the address like the first two methods. They just borrow an IP address from a pool of addresses. So each ISP is going to have distributed DHCP servers across its network. And so every client that uses that ISP server who wants to get onto the internet will automatically send out a DHCP discover requesting an IP address, and it goes to all of the DHCP servers within the network. All of the DHCP servers that have available IP addresses will then send their offer back to the client, and the client must decide which ISP or IP address it wants to use. And once it selects one, it will send out a DHCP request. Now, this request goes to all the DHCP servers so that they know if they haven't been selected, then they can still have that IP address to use elsewhere. But the one that is selected will then assign that IP address back to the client, and then the client uses that IP address throughout the exchange with the internet. So DHCP dynamic allocation certainly helps us stretch out the limited number of IP version 4 addresses that we have. But what about when we have IP version 6, which has a 128-bit address? That's more addresses than we will probably ever need on the internet. And so why would we need a DHCP service at all? And the answer is quite simple. Number one, you'll have so many devices that you'll still want to have a way to automatically allocate all of your IP version 6 addresses to what could be many, many more devices, especially if you talk about the Internet of Things. The other thing is that you'll still have a dynamic allocation requirement because there'll be a lot of users who may swap out computers. And so they certainly don't want an IP address that's specific to their computer. They want one where they can just go ahead and borrow one whenever they need to. And as long as there's always an IP address that's available, then there would be no reason to have a permanently assigned IP version 6 address. So there is for those and many other reasons, there is the DHCP version 6 that's applicable to IP version 6. The purpose of the Network Address Translation Protocol is to map internet addresses to private intranet addresses. And so let's take a look. Here we have an intranet, or a private internet, still running the IP protocol, and outside we have the real internet. So, of course, if you're on an intranet, an organization that's running its own IP addresses, you may still want to go out to the real internet to do some e-commerce or do research. And so what you would have is a gateway or a server running the network address translator between these two. And all it's going to do is map your internal IP address to your external IP address. So why is this important? Well, first of all, you can see that any kind of threats, cybersecurity threats from the internet, has to go through this gateway with NAT running on it before it can get into the intranet. And so isolation from external threats posed by the internet is a good thing. And the second, if you have a limited number of IP version 4 addresses on the internet, well, then you don't have to use them on the intranet or private network. You will have the private network that has its own IP addressing scheme. And so therefore, all you really have to have is a pool of addresses for those individuals who want to cross the NAT into the real internet. So you actually extend the life of limited IP version 4 addressing. Also, if, say, for instance, you had a service provider that was doing nothing but IP version 6, well, if you were connected directly to the internet service provider and you had to get IP version 6 addresses for all of your devices, then you would have to swap out all of your devices. And you'd have to do the upgrade as the ISP did the upgrade. Well, being able to use the intranet isolated from the NAT tells you that, hey, I can run my old IP version 4 internal addressing system, and you can go ahead, ISP, and upgrade to version 6, but I don't have to upgrade with you. So there's some isolation as far as having to keep up with the ISP. And then, of course, it makes it much easier for an organization to say, hey, I'm going to change from one ISP to another ISP. All you really have to do is make sure you're connected through your NAT server. You don't have to go into all of your devices within your private IP network and get assigned new IP addresses based on the ISP. There's a couple criticisms of the Network Address Translation Protocol, and one is that because you're changing IP addresses between the private network and the internet, you're not a true end-to-end connection or end-to-end circuit. The other one has to do with certain protocols, and in particular IPsec, which has integrity problems crossing the NAT server. So with IPsec runs on two different modes. One is a transport mode, in which only the payload is encrypted, and the other one is the tunnel mode, in which both the header and the payload are going to be encrypted. Now, one of the things that IPsec gives you is authentication. So it has AH authentication header, in which a hashing algorithm is placed over the addresses, and so as this datagram crosses the NAT, of course, the hashing algorithm, since the addressing is going to change, the hashing is going to be different, and so therefore it's going to see that this is an error and just throws out the datagram because of an integrity issue. With the encryption service, the ESP, or the encapsulating security payload, in the transport mode, where only the payload is encrypted, could impact the transport layer protocol, which might be encapsulated. And then in the tunnel mode, the entire datagram is encrypted, also leading to integrity errors. Distributed across the internet are servers that run the DNS protocol, and this protocol actually runs the domain name resolution, and this domain name resolution will actually map uniform resource locators such as www.gmu.edu to an actual IP address. And this is pretty handy for us because we can usually remember a URL better than we remember the address of the specific site that we're trying to get to. Now, there's a hierarchical way of looking at the DNS, and that starts off with the root domain, and the root domain is going to be run by IANA, which is the NGO that distributes IP addresses. And then below the root domain, we have top-level domains, and as you can see, you probably recognize a few of these, like .edu and .com. And then if you look on this chart here, you can see what these top-level domains are and who the sponsoring organizations of each are. And there's more than just this on the list, but this is just a sample. The next hierarchical level is going to be the domains themselves. And so in this case, we might have a www.gmu.edu for the university. And of course, you know, the university has many web pages or subdomains associated with it so that you could actually search out, as an example, academics or student life. So this is a hierarchical way of getting to the information that you really want in the area that you want very quickly. Now, one of the big benefits of having a DNS is that occasionally organizations will change ISPs. ISPs have their block of ISP addresses. So if, say, for instance, George Mason was to change over to another ISP, they would have new sets of ISP addresses or new sets of IP addresses. And so instead of having to remember the changes of all the IP addresses, if you have gmu.edu, and that's how you go and search for the university, then no matter what ISP George Mason happens to be working with, it's really transparent to you because it'll just automatically be mapped to the ISP that's serving the university campus. So you can think of it as a telephone book in which your name never changes, but your phone number may change. And so as long as you get the updated version of the telephone book, somebody will be able to look up your name and then give you a phone call. There are many protocols that are used on the internet, but the last one that we'll be talking about will be the Internet Control Message Protocol, or ICMP. Now, of course, routers are smart and they need to be updated on their routing tables, and so therefore you have the border gateway protocols. We also have an Internet Control Message Protocol, which essentially just sends messages to all the devices on the IP network. And the information that they send is information regarding network conditions, such as any kind of partitions that might be out there, congestion, what IP addresses might be unreachable, if there's a gateway or a destination that has buffering issues, or anything that might be pertinent to routing information used by the routers themselves. And so the ICMP messages are going to use the standard IP format. And so here you can see the IP version 4 format. And what they will do is they'll add on an extended header and message tagged along underneath the IP header itself. In this section, we talked about the differences between the IP version 4 and IP version 6 data formats. We talked about the Border Gateway Protocol, which was a way to actually have routers share routing information both within the autonomous network and external to the autonomous network. We talked about the Address Resolution Protocol, which was a mapping between Layer 2 MAC addresses and IP addresses. We also talked about the Dynamic Host Configuration Protocol, which was a way for an ISP to actually distribute IP addresses, as well as a way for users to borrow IP addresses, thus helping to extend the IP version 4 addressing. And then we talked about Network Address Translation, which was a way to map addresses from a private intranet to the actual public internet. And by doing so, you help isolate the private network from the external internet, as well as you extend the number of IP version 4 addresses that you could spread. And then finally, the domain name system, the name DNS, was there to do address resolution so that we could take a URL and then it would translate that to an IP address. And so therefore we didn't have to memorize the IP addresses. And then just one more, the Internet Control Message Protocol, which was a way for devices to share information regarding the network condition. We're going to be talking about other protocols that complement the Internet Protocol. We're going to talk about the transmission layer protocols that are typically used, which are Transmission Control Protocol, or TCP, and then the User Data Protocol, UDP. And then we're going to talk about multi-label switching and how it improves IP services. So what's the purpose of the protocols at the Transmission Control Layer, or Layer 4 of the OSI reference model? With the IP addresses, which are end-to-end, you know that the data has actually made it to its destination. And so therefore, you don't have to have addresses to try and get it any further to the destination. You already have the information at the destination. But, of course, all our computers and servers are multitasking. So the idea behind the transmission control layer is to identify those applications that the data belongs to, since we know that there's going to be more than one application running on your computer or server. And so that's the role of TCP and UDP. And as such, they have what we call source and destination ports. And these source and destination ports will identify the actual application that this data belongs to. So when we look at the source and destination ports, we are not looking at an address, we're looking at the application itself. Now the format that you see on the left here belongs to the Transmission Control Protocol, or TCP, different than UDP. So we'll be talking about TCP first. And TCP is a connection-oriented protocol, which means it establishes a connection using overhead prior to the exchange of data between the two communicating endpoints. Now, when you talk to your ISP, sometimes they'll be talking about the socket. And so what is the socket? Well, the socket is a combination of the IP address of the device plus the port assignment which identifies the application running that the data belongs to. So let's take a look at this TCP format. Of course, we talked about the source and the destination ports, and these are going to be 16-bit assignments. And because TCP is going to be connection-oriented, it's going to worry about the proper sequencing of all the segments being received by the destination. So, of course, you're going to have a sequence number, and then because you're going to have flow control, you'll also have an acknowledgement, and we'll talk about that in the next couple slides. So let's take a look at just a few of these fields. Control bits. So these are control bits, and they are here. They're 1 bit long for each one of these controls, and we're only going to be interested in 3 of these. One is the acknowledgement bit. So if there's a 1 in this position here, that is sent by the destination to the source, and it tells the source that, yes, I've received the data successfully, go ahead and send the next set of data. And then we have the synchronization request. And so the synchronization is used in the 3-way handshake to establish the connection between the source and destination. And then once that exchange of data has been completed, then we have a finish request that is a control bit that indicates that we're no longer having to send any more data. We're ready to close out the actual connection. The window field is extremely important. And it's a 16-bit window, and each bit represents an octet. And so the window essentially sets how many bytes of transmission can take place prior to acknowledgement having to be received by the sender. So why is this? Well, first of all, when we look at TCP, TCP is impacted by network congestion. And so if it starts to see a lot of timeouts or a lot of delays in the data that's coming from the source to the destination, it determines that the cause is probably network congestion. And as a result, it will start to change the size of the window. So obviously, when you first start off a transmission, you'll have very small window sizes, which means you're not going to be sending that much data. And then as you get successful acknowledgments back from the destination, you start to increase the window a little at a time, until finally, if you're at the full size of the window, then that's the maximum exchange rate or data rate that you're going to be able to achieve. However, if you start to lose some data, maybe your timeout on the destination side has expired, then TCP thinks it's because of network congestion. There's just too many people using the network at the time. So therefore, it starts to reduce the size of the window until it starts to receive successful acknowledgments from the destination once again. Now, the whole idea here is if you have a lot of users or a lot of connections through TCP on a network, if you have network congestion, then all of those connections will start to reduce the amount of data that they send, thus alleviating the congestion on the network. And then once the congestion is alleviated, then they can start to increase the window size, increase the amount of data that they place onto the network. So the window size is critically important and is used for network congestion. And of course, we have a checksum, and the checksum is applied to the total TCP segment, and then, of course, the payload. As you can see in the table on the right here, we have a list of port assignments and the applications that they belong to. Now, this is just a part of a list, example of a much larger list that you could go ahead and Google and see how many port assignments there actually are. And matter of fact, organizations could actually create their own port assignments to their own applications that they want to send the data up to. Now, this table, of course, port assignments are used for both TCP and UDP. So this is a diagram that just kind of shows you how the protocol stack actually works. And so you can see that the only real physical connection is whatever you're connected to at the physical medium layer, or layer 1. Of course, all of these other connections that you might have, dead link, network, or transport, are all going to be logical connections, so you're not actually connected physically. So the only physical connection you have between any nodes or devices is going to be the wire, or the RF, or the fiber optic. So the source will have its data transferred from the application, and then as it goes down the stack within the computer, the TCP header will be attached to it, identifying the source that that data belongs to, and then, of course, to the IP header, which identifies not only the source but the destination that this data needs to be sent to. And then, of course, if you're on a local area network, then you're going to have, say, Ethernet envelope around your data. And then finally, when all that is ready to go, it becomes line-coded and then travels the physical medium until it reaches its destination. And then the reverse happens. The Ethernet header will come out. The IP address comes off, the TCP header comes off with the port assignment to the specific application at the destination that that data has to go to. So let's talk about normal establishment of a connection and termination of a connection using TCP three-way handshakes. And so we first take a look at establishing a connection, which is here on the left. And so the sender who wants to establish that connection will send a sync message. Of course, that's the sync control bit on a TCP segment to the recipient. And if the recipient wants to establish that connection as well, it will send a sync acknowledgement. And then finally, the sender will then say, okay, I've acknowledged your acknowledgement, and so now you're ready to send actual data. When you're ready to terminate a connection, you have to have both sides agree to the termination of the connection. So let's say the sender wants to terminate, we'll send a FIN request to the recipient, then the recipient will acknowledge it, but then we'll send its own FIN request stating to the sender that it's ready to terminate the connection, and then the sender sends an acknowledgement to that FIN request, and then the connection is terminated. So let's say we've established a successful TCP connection. Let's take a look at three scenarios. One in which we have error-free transmission. Another one where we have actually a lost transmission from the sender to the receiver. And then the last one where the acknowledgement back from the receiver is lost. So we'll take a look at the first one first. So we see that we're going to be able to send 100 bytes of data prior to expecting an acknowledgement. So that essentially tells us that our window size equals 100 bytes. So we send our 100 bytes, and once we've sent our last segment within that first 100 bytes, we start off a timeout period or a timeout clock. And this timeout clock essentially times out when we expect to see an acknowledgement back. If we don't see an acknowledgement back once the timeout clock has expired, then we assume that either the data or the acknowledgement has been lost, and so therefore we're going to send everything back. We're going to retransmit everything that we think has not been received correctly. But in this case, because we're talking about error-free transmission, we get an acknowledgement back, and the acknowledgement essentially identifies what the next segment expected by the receiver is going to be, and that happens to be 101 in this case. So the sender says, okay, the first window was sent successfully. I'm going to send the second window, and I'm going to send 100 to 200. And then that is received successfully, so the recipient sends an acknowledgement back with the number that coincides with the expected segment of the next transmission. Now let's see what happens when we have a lost transmission. So in this case, the sender tries to send the first window out. But of course, the second segment of the first window gets lost. At the same time, the sender will start its timeout period clock. And so, of course, since the entire window has not been received by the recipient will not send back an acknowledgement. And so the clock expires, and then once the clock expires, then the sender thinks, well, you didn't get my window at all, so I'm just going to repeat the transmission that was not received or acknowledged. And so this time we're successful, and the recipient actually receives the entire window and then sends back an acknowledgement with the next segment expected. So finally, let's take a look at what happens when we have a lost acknowledgement back from the recipient. So in this case, the entire window is transmitted correctly and received correctly by the recipient. So the recipient actually tries to send the acknowledgement with the 101, the next segment expected. However, somehow it's gotten lost in the network. And so, of course, this timeout period is going to expire because it never receives the acknowledgement, and so then decides that it needs to resend the entire window again, not knowing if the lack of the acknowledgement was either because the first segment or the window was not sent properly or lost in the network, or whether the acknowledgement was lost in the network. And so once this repeated window gets transmitted and received correctly, then once again we have an acknowledgement from the receiver. So let's see what the maximum throughput through a TCP connection is. And so we can use this formula here. And this formula essentially says that the maximum throughput is going to equal the TCP window in bytes divided by the data latency of these data actually traveling from the sender to the receiver. And so the formula tells you that if you increase the window size, you're going to increase maximum throughput. However, if you start to have a lot of latency within the network, maybe caused by network congestion, then your maximum throughput starts to go down quite a bit. So let's do an example, a real quick example here. And let's say that in this case, we had 100 bytes. So we're going to say 100 bytes. And of course, we know that there's going to be 8 bits per byte. And then a typical latency through the network might be 30 milliseconds. So that'd be 30 milliseconds. And of course, we could always turn that into 30 times 10 to the minus 3 seconds. When we do this math, then we come up with a maximum of 26.67 kilobits per second. Not a heck of a lot, so you can see that there would be a reason why we would want to increase the window size in order to achieve maximum throughput. Unlike TCP, which is connection-oriented, UDP is connectionless. So UDP doesn't have any kind of overhead to create a connection. It's just going to send data out there. So the data, it's not going to worry about sequencing of the data. It's not going to worry about any kind of guaranteed delivery. It's essentially there so that for some of those applications that don't really require all the processing that maybe a TCP segment would require, that you could actually be a very, very fast protocol. And so as you can see from this header, there's really not much overhead here. You've got a source and destination port, you have the length checksum, and of course the payload. So where would you use this? Well, obviously you would use it where you have a lot of sensitivity to any kind of delay, such as gaming, or you have real-time voice over IP that you're trying to support. Then, of course, other types of protocols like routing information protocol, like a simple network management protocol, and of course DNS, which we saw earlier. Let's take a very brief look at a multi-protocol label switching network. And so we can see this in the diagram. It's an MPLS network. And so an MPLS network is one in which a service provider will add quality of service to IP network users. And so as a result, if an IP packet goes into an MPLS network, it's going to be affixed with a label, and this label is going to determine the path through the network. So if you have some quality of service requirements, then you can be assured that this label will find the best route through this network. Now, however, once it leaves the network, the label gets stripped out, and then it just becomes a normal packet again. So the quality of service is only through the MPLS network and during the time which the data is in the MPLS network. And you're going to pay an extra fee for it, but at this time, when we looked at the internet and the internet being something where there was no quality of service and no guarantees because it was a connectionless best effort type of network, MPLS provided the solution for those who really wanted to have some kind of service level agreement or quality assurance. So in this section, we talked about TCP and UDP. We talked about the source and destination ports and how they align to the application running on the server or the computer. We said that the TCP was connection-oriented, creating a connection through a three-way handshake, whereas UDP was connectionless and just sending data with the UDP header information to get to the right application at the destination end. And then we did a quick definition of what an MPLS network is.